So now that we know the basics of equilibria and that it's a chemical reaction that's reversible and happening in both directions at the same rate, so it looks like it stopped, but it's still going back and forth at the same rate, we're going to look at ways that that equilibrium might change once it's established. So sometimes we get to an equilibrium and it looks like it stopped and it stays like that. But often there will be some shifts and stresses that can happen to that equilibrium, and we want to be able to predict how the equilibrium will change. And Le Chatelier was a French chemist who worked on this. He came up with a way to predict how different stresses will affect an equilibrium. Le Chatelier said that when a chemical system at equilibrium is disturbed by a change in property, we'll talk about what that could be, the system will adjust so that it will oppose the change to try and get back to its equilibrium state. So the equilibrium always wants to maintain that equilibrium state, and it will oppose whatever change we have. Let's talk a little bit about what that means. So another way to think about Le Chatelier's principle is that if you apply a stress to a system, it's going to shift to reduce that stress. And what we mean by stress is a property change, like adding or removing a substance. We might add or remove heat, and we can even change the pressure as well. And then what the shift means is that the system will temporarily favor the forward or reverse reaction to accommodate the stress, and then it will just do that temporarily and equilibrium will be reestablished. Let's actually look a little bit more in detail what shift means. My normal equilibrium will be going back and forth with the same rate so that no products or reactants are being made overall. There's an equal amount and it's going back and forth and back and forth. So the rates of the forward and the reverse reaction are equal. When an equilibrium shifts either to the reactants or the products, what it does is it changes the rate, the rates change a little bit and they're no longer equal. So a shift to the products means that the forward rate is going faster. There's still a little bit of the reverse reaction happening, just more slowly. So overall, we're going to have products made and reactants used up to make those products. Similarly, if I have a shift to the reactants, the reverse reaction is going to be faster or favored, and then the forward reaction will be slower. So overall, I'm going to use up my products for B to make my reactants or A. So we're going to use this concept and apply it to some stresses that might happen to an equilibrium or that we might intentionally use an equilibrium to get it to shift one way or another. The first stress we'll look at for an equilibrium is if we add one substance, and we'll use the same process if we also remove a substance. We're just going to use this generic equilibrium at the top and see how it will be affected by adding a gaseous substance to the container. We're going to look at what our actions are and also what the system will do to react to that and how it can shift to react. So if we add gaseous X to the container, we're actually increasing the concentration of X. The system always acts to oppose this, so it's going to want to decrease the concentration of X. And then the system will shift to accommodate that and to decrease the X. So if I increase concentration of X, the system will want to decrease it. Remember, it can shift either towards the products. So that means it's going to make more products. And it would also use up the reactants if it's making more products. Or it can shift to the reactants where it would make reactants And in that case, it would use up the products to make the reactants. If it's going to shift to get rid of the X, then it's going to have to shift towards the products, because if I do that, then I'm going to make more products, but in making more products, I am using up X. So we would say that this equilibrium is shifting to the products or to the right. We're also going to graph what happens. We will start with a graph where we put some initial concentrations in right at time 0, and the reactants both reacted away, made some product Z, but at this section right here, it is at equilibrium. So my equilibrium here is highlighted in yellow, where the concentrations aren't changing. The reaction in this section is going back and forth between reactants and products at the same rate. We're going to add in the shift. So we want to show how we increase the concentration of X. So I'm going to actually just show that in red, where we spike that concentration, it's increased. That was our stress that we acted on the system. And then we'll also show the shift, how the system responded to that stress on the graph. So when we are graphing, if possible, we want to show the stress. We won't always. And it's what we have here, an increase in the concentration of X. And we'll also show how the system reacted by shifting. If it's shifting to the products, we will see an increase in the products, a temporary increase until it gets back to equilibrium. So I'll show that in blue. And then what's happening with my reactants is they're being reacted away to make the product. So I'm going to show their concentrations decreasing. I'm going to try and keep it around the same time frame. And this will just happen temporarily, and then it'll be back to equilibrium. So we'll draw that flat area where it's now reached a new equilibrium. That should be horizontal. It's a little bit hard to draw horizontal here. And that means that we've reached a new equilibrium. Those are equilibrium concentrations again. And I'm going to actually highlight that as well in yellow, because that's my equilibrium. And that's how we graph. There are just a few notes to finish off before we look at the next stress that we can add to a system. Some things to just know when we're using Lechatallier's principle by adding or removing substances is that if we're adding a gas or aqueous substance from my reaction, it will affect the equilibrium, and you'll see that stress of the one that you added, and then you'll see a shift, but it will not affect the equilibrium if you add or remove a solid or liquid substance. And the reason is that the solid and liquid substance concentrations cannot change, so they won't affect my equilibrium. Another thing to note is that if we add or remove a gaseous substance, you can see that we have that stress and then a shift, and we get these new equilibrium concentrations. So the equilibrium concentrations will be different, but K will be the same. So if we took the ratio of product concentration of products over reactants, we'd still get the same K putting in these concentrations as we would putting in these concentrations. So that constant is not affected by this. Now we can check out some other stresses that we can add to our equilibrium. The next stress that we're going to look at is if we increase the temperature of the container. So that means my equilibrium is going to have more heat. Whenever we're working with temperature or heat, we want to put the heat term into the equilibrium so that we can treat it like we did adding or removing one of our substances in the equilibrium, and it makes it a lot easier for us. In this equilibrium, I'm adding heat, so I'm going to list that as my action or stress. My reaction of the system, so how the equilibrium wants to react to that upset, is it's always going to oppose that. So it's going to want to decrease the heat, and it will shift to do that. There are two ways that my equilibrium can shift to decrease the heat. It could go in the forward direction and make more products and use up reactants, or it could go in the reverse direction, and in that case it would make more reactants and it would use up my products. Since I need to get rid of the heat, my reaction is going to go in the reverse direction or shift to the reactants. If it does that, it's going to be making my reactants and then using up my products. And because this is an exothermic reaction where the heat is in the products, it's going to shift towards the reactants or away from that heat and use it up. For every reaction, this might be a little bit different because you might increase the temperature or decrease. So you would have different shifts depending on if you're increasing or decreasing. You would have different shifts depending if the heat is in the reactants, which means it's endothermic, or if it's in the products, which means it's exothermic. So depending on the reaction, you're going to get different things. But if you go through the thought process of what is the stress, how is the equilibrium reducing that stress by doing the opposite, and which direction can it shift to do that, then that will help you predict the correct direction, no matter which type of reaction or what you're doing with the temperature. And the last thing that we want to do is also to graph our temperature change. The temperature change looks a little bit different when we graph it because we don't have heat on my graph. We can only graph the concentrations of matter, not energy. So we can't graph the concentrations of heat. We're not going to be able to see this stress. We won't see that increase in heat. We're just going to see a shift. So this is actually a clue that you have a temperature change on a graph if you just see a gradual shift, not a spike of the stress. So I'm going to show it making more reactants. We are starting at equilibrium here, and then we'll show it making more reactants as the shift because I can't see the stress. So here I'm starting at my equilibrium. I'm going to show the shift of the reactants gradually increasing. That should be slightly curved. And the Y would as well. And then my products are going to decrease because I use up products to make reactants. And they will, sorry, I'm just going to redo that, decrease until a new equilibrium has been reached. And then I will have a flat portion of my graph, and that will be the new equilibrium that's established after my shift. Oh. So those should be nice and flat. My drawing's not perfect, but those lines should just look like the equilibrium lines here and be nice and flat. So these ones should be nice and flat, just like that one. And I'll highlight those to show that those are the same as before. They're at equilibrium. It's just a new equilibrium that has been established. One thing that you should note about temperature changes is that the K does change with temperature. So you won't have the same K when you have an increase in temperature or a decrease in temperature. So I'll just put a note here at the bottom. that when you do have a change in temperature, there will be a change in K. And we will look at one more type of stress that we can add to a system at equilibrium, and that will be a change in pressure of a gas, where we actually change the pressure, and it will, if we increase pressure, reduce the volume, or vice versa. So our last stress that we're going to add to our system at equilibrium is a change in pressure. This will also affect the volume as well. I just like to mention before we do this one, when we're talking about pressures and volumes, this will actually only apply to an equilibrium system with gas molecules. So the pressure increase will only apply to the gaseous molecules in the equilibrium. So I like to imagine that the equilibrium is happening in a container where we have a where we can change the pressure. So like a cylinder with a piston, or it's kind of like a plunger that you can push down and increase the pressure on that piston. And if I increase pressure, I'm going to be making a smaller volume. If I do the opposite, if I reduce pressure or pull up on this piston, it's going to make a larger volume. And that is actually what I'm doing with my stress. So I'm squishing these gas particles closer together, so there's more of them in a smaller, well, there's the same number in a smaller space, so there's more concentration there. So this one, we do have to think about those gas molecules and the space that they have to get our reaction. So the system is going to want to reduce the number of gas molecules in the space. That constant is going to want to reduce that concentration. And it can do that by shifting to either the products or the reactants. So what we're going to have to do is look at my equilibrium and look at which side has more gas molecules. And if we've put more gas molecules in a small space, it's going to shift to the side with less gas molecules. In this equilibrium, my left side or reactants have 2 gas molecules. And make sure you include the coefficients. If I had coefficients, I would count, say this had a 2 in front of it, I would count that as 2 plus 1. But here we have just 1 X and 1 Y. So that's a total of 2 gas molecules. And in the products, I have just 1 gas molecule. So there are less on the product side. My reaction is going to shift to the product side then. This again will change with every equilibrium. So you'll have to do this analysis here with every equilibrium by seeing which side has less gas molecules, or if I did the reverse and made the volume bigger so those gas molecules had more space, then it would actually shift to the side with more gas molecules. So in this case, we have the side with less gas molecules will be the products. And that's how my equilibrium will react to this particular pressure stress. Again, if you have a different equilibrium where you might have different numbers of gas molecules, then you would see a different shift. So it's good to always do this analysis to make sure you get the right shift. The other thing that I would just want to mention with this is every once in a while you get an equilibrium where they have the same number of gas molecules on both sides. That equilibrium actually doesn't even have the ability to react to a change in pressure because it can't make more or less molecules. So it wouldn't shift if they're the same number on each side. And lastly, we want to graph this as well. We will start with our equilibrium at after we've had some initial reaction. And we want to show, in this case, we can show our stress. We can see here we have all of these gas particles squished into a smaller space. So all the concentrations of these have increased. So this is the only type of graph we can tell it's a pressure and volume change, because all of the substances will have a spike in concentration. So that means that we squish them into a smaller volume. So we can see our stress, but it will show in all of the substances that are gaseous because they got squished into a smaller volume. So we have our shift, and then we can also, we have our stress, and then we can also show the shift where it will shift to the products to make less gas molecules, and we'll do that in blue. So my products will increase in concentration, and then we'll get to a new equilibrium. So that should just be a little curve up. And then the reactants are going to react away and decrease. So they're going to go down in concentration. And I will have after a shift, it will establish a new equilibrium. So we'll have a nice horizontal, or as horizontal as I can draw it, equilibrium with constant concentrations after that shift. So this is my new equilibrium here, highlighted in yellow, and this blue, was the shift of the reaction. One other thing, we do want to just make a note about the K for these, for pressure change. When we have changes in pressure or volume, my Kc for the reaction won't change. And that's because the concentrations will change. So I'll get a new concentrations to put into the K, but overall that ratio of products divided by reactants does not change. And that is the basics of how to do shifts in equilibria using Le Chatelier's principle.